very good evening to all my respective professors and our today's expert speaker and to all the participants. So, Center of Excellence um in Safety Engineering and Management welcomes all the participants to the Weekend Talk program. So, this program is conducted under Azadi Ka Amrit Mahotsav, 75 years of India's independence. So, we will start our program with the beautiful Sanskrit shloka. Asatoma Sat Gamaya, Tamasoma Jyotir Gamaya, Mriturma Amritam Gamaya, which tells us and leads us from ignorance to the truth, from darkness to the light, and from death to the immortality. So, this is our 22nd Weekend Talk program. Now, myself, Shinjana Chaudhary, along with other moderators, Mr. Shobik Dash and Mr. Ashish Garg and Mrs. Mohmitra from Tata Steel, would like to welcome our today's dignitaries on the virtual dais. So, Professor J. Maiti, our chairman of CoE-SEA, and Professor Obi Krishna sir from the convener of the Weekend Talk program, and our expert speaker, Professor Shuprakash Gupta. So now I would like to welcome Professor J. Maiti sir to welcome our today's expert speaker, Professor Shuprakash Gupta. Formally welcome our expert speaker. Over to you, sir. Thank you.
Thank you, Shinjana. Thank you, Professor Gupta, for accepting our request. And you accepted to give a lecture on a very important topic, that is human error. And Professor Gupta is currently professor in the Department of Mining Engineering, Indian Institute of Technology, BHU. And he did his bachelor in mining engineering from Bengal Engineering College, Shibpur. Now it is Indian Institute of Science, Engineering and Technology, IIEST Shibpur. Did his master from IIT Kharagpur, and he was my batchmate in the master. And he did PhD from IIT Kharagpur in the area of machine reliability and maintenance. And thereafter, he has been in BHU for last 25 years. And he is very much known in the area of reliability, maintenance, and human error. In India, if we say people working in the area of human error and machine reliability, particularly in the mining sector, then I think the topmost name will be Professor Gupta. His approach is not applicable to mining only, it is a generic one applicable to all industries, all sectors, all kind of problems. And he visited several countries, and he was in University of Lilua with Professor Uday Kumar for several months, and also at different times. He visited IIT Kharagpur several times, and he is an expert speaker as well as expert in this particular area. And you will learn from, you will know from his talk today that his expertise. Actually, I want to tell you one thing. Basically, when I thought of that, I will be inviting somebody to talk on human errors, then the first name came to my mind is Professor Gupta. And because of only single reason, not that he is basically doing in this area for several years, research and teaching and guiding and consulting. I listened to him in one of the DRDO meeting where he was giving a lecture on human error quantification. And it was so fantastic a lecture. I still remember that lecture, and I am sure that you all will be extremely benefited and will be enjoying giving today's lecture on human quantification and prediction of human errors for industry jobs, issues, challenges, and future direction. With this, Professor Gupta, I welcome you to the Weekend Talk, and you know that our Center of Excellence in Safety Engineering Analytics is 1 year old now. With all of your support and cooperation. We are doing our best, and we would like to do even much better, much more activities with all of your supports, including the not only support from you, from all the participants who are regularly participating and enriching us every day. Thank you, Professor Gupta. Please start your lecture.
Thank you, Professor Maiti. Although you called me an expert in the field, but I don't feel myself that an expert. I am just a learner of this area. Last few years, I am learning that subject. Thank you, Professor Krishna, and thank you, Professor Bhattacharya. Thank you, Sanjana. The topic has already it has been displayed, that quantification and prediction of human error in industry jobs, the issues, challenges, and future directions. So, if we look at the advances in, if we see the advances in the last few decades, there was a tremendous advance in the technology, the engineering, and in the quality of materials. So, all those things they have a good impact to upgrade the reliability of a system. But there was not much changes in one component of the system that is very essential, that is the human. So people that continues to be the significant contributor to the system failure. Although it is very difficult to obtain a valid values, but the estimate agrees that almost 60 to 90% of the accidents are due to the undesirable human behavior. So you can see that there's a huge impact of the human behavior on the accidents as well as the system safety. So this is largely due to one of the humankind's weakness, which can be summarized in a truism familiar to most in the human factor fields, that conveys the basic fact that people, even the professionals, even the experts, they make mistakes. That is the two R is human. Now, people, we cannot think a system without people. So they are the vital component to a system, and the best human performance that is very, very essential for productive, efficient, and safe system operation. Humans are involved in all the phases of a system life cycle. It starts from the conceptual design stage of a system, because when we are talking here about only the man-made system, not the natural system. I'm not talking. So man-made system means the human has made the system. That means human is primarily responsible for the failure of the system. So they have done some error either at its design stage or maybe in its during its construction or its fabrication, during its testing or validation, or during its operation or maintenance, or even during its disposal or removal. So even the human error, or we can say that system is susceptible to human error for the automated system also, because automated system also there is some human interaction is there, or even the system has been designed by the human. So during the design stage, if there is any error, so that may manifest during its operation. Now, question is, what is a human error? Now, human error, this is also one type of human action. Now, any action, whether we can classify it as an error or not, that is basically the case specific. Any wrong action can be justifiable in some system until it does not lead to the occurrence of any incident, and later it is categorized and human error. So same action, until it is creating any incident, it is normal. But if it results in an incident, then we will categorize it an human error. So we can say that human error is a subset of human action. It is also a subset of human action. Error is also one type of action only. So human action, that is the response initiated by the sensory triggers that do not produce the desired result, that can be termed as the human error. So we can develop the concept of human error with the background of information processing. So when one is encountered with a particular environment, his sensory organs continuously scan the surroundings or the environment, and it continuously get input through its sensory organs. Now, on the basis of the input, or you can say that if any things depending on the values of the input, a response the human will give to the environment. So human response, we can say that this is a sum total of a series of functions. So these functions may be your attention, then your perception, then your memory retrieval, then cognition, then your decision making, and all these actions are activated through the sensory triggers. And under or over performance of these functions change human responses into human errors. So this is the concept of human error with the background of information processing. Now, with that, how we can define the human error? So the definition given by the NASA, that is either an action that is not intended or desired by the human, or a failure on the part of the human to perform a prescribed action within specified limit of accuracy, sequence, or time that fails to produce the expected result and has led or has the potential to lead to an unwanted consequence. So this is also a action or reaction against the input which a person received from his surroundings or environment with the help of the sensory organs. Now, different researchers or different experts in the field, they have defined human error in their own way. But there is a common things between the definition given by the different experts. There is a common feature. That is, human error is a label given to an human action or reaction that has negative consequences or fails to achieve the desired outcomes. So, whatever the cases, how it has been defined, but this is the common feature that human action or reaction that has a negative consequence or it fails to achieve the desired outcomes. Now, when we talk about the human error, so naturally the human error, this is a measure of performance, which in turn the measure of human reliability. So when we talk about the system reliability, we talk about the reliability of the entire systems, that is the reliability of the hardware, reliability of the software, and people or human, they are a part of the system. So when we are designing a system for its reliability, so we must design the system, we must take into account the human reliability aspect also. So hardware and software reliability, that has been well embedded into the design and the analysis process, while human reliability is commonly ignored. Most of the system, the human reliability part, these are not get due importance. This is what I feel, maybe due to the lack of information, especially in the lack of data. So human reliability is what indicates the probability that human will perform as intended over a specified period of time and under specified environmental conditions, and the probability that the system reliability and availability will not adversely affect the human action, or system reliability and availability will not be adversely affected by the human actions. So human performance that can lead to the accomplishment of the work objectives, and if the human performance is ineffective, in many places they may cause injuries or fatalities, damage to the hardware or the facilities, or even cripple the system. So, adequate analysis of the human reliability is critical from the system safety or preventing the large scale damage. Now, human reliability It is a very comprehensive and it has a very comprehensive and structured methodology. It applies qualitative and quantitative methods to assess the human contribution to the risk. More specifically, we can say that human reliability, it applies a series of methods, and these methods are used to identify and to predict human error in certain task conditions which impact the system safety. And then the human reliability analysis is evaluate the potential risk of the errors, then identify the causes of the errors, and then finally it minimizes error occurrences using different error reduction techniques. Now we can give the basic structure. This is the basic structure of human reliability analysis. Now, depending on the problem at hand, so which is basically the event selection, the task analysis that identifies human errors. Task analysis, it identifies the human errors in the task, that is the error identification. Now, to better understand the cause or performance influencing factors, the human performance influencing factors, the vulnerabilities of the systems to human error, recoveries, and possible risk mitigation approaches, errors are represented in models, that is the error modeling. So human error in the human reliability analysis, the human errors are modeled as the contributor to the initiating events. So errors, basically these are not the events, they are contributor to the events, the event that may initiate to system failure, or the consequence of the human error, in the other way we can say, that may lead to the system failure. And the consequence of the human error that serves as the initiating event for the system failure. So, in the human reliability analysis, the initiating events of the system failure usually generate outside the scenario and are provided to the model from other sources. So this representation, it helps in evaluation of the human error impact on the system. So it is possible to assess human reliability qualitatively as well as the quantitatively. So once it is assessed, then we can think about the management of the error. So in the latter stage, managerial decisions are made for error management to improve system safety after an impact assessment of the error. So all these process, this is basically an iterative process, and every stage stages of the iteration, we try to improve more safe and better reliable systems, which are not affected by the human error. Now, human error, this basically encompasses the use of system engineering. This encompasses the use of system engineering and behavioral science methods to evaluate the interaction between the humans and the rest of the system components and enable the management of human error to optimize the system reliability and to reduce risk. So human reliability analysis, which is basically starts from the error identification, that tries to find the answer of a set of questions. That is, what human actions can go wrong, which are the human failure consequences if some action go wrong, that is, if human error occurs, what will be its consequences, which human PIFs influence human reliability the most, what is necessary to improve human reliability, to avoid or to prevent human error. So human reliability analysis basically finds the answer of this set of questions. Now, quantification of prediction of human error. Now, all the quantification techniques for the human reliability that involves the calculation of human error probability. Calculation of human error probability, which is basically the measure of human performance or human reliability. So this is through a series of steps is involved in the error quantification. And quantification methods which will be used for the quantification, that basically depends on the resources available. What are the resources available? Basically, this is the time and the money. This also the level of expertise of the analyst, and obviously the availability of the data. The data must be sufficient to allow the analyst to estimate the frequency with which the errors may occur and the number of opportunities for these events. Now, what are the sources of the data? The data may come from the databases. You can get the data by simulation or by expert judgment. So these are the sources of data. Now, in the human reliability analysis, it has passed through a different generation. In the first generation HRA methods, these methods don't put much thought about the complexity of human behavior, and it has we can say the modeled the human reliability uh, just like an other equipment. So it thought that like a machine, this is also a part of the system and how the machine fails. So similarly, the error occur in the human components. So here the human error probabilities that has been used the data set which mostly has been generated in the laboratory as well as the PIF multipliers. Then we come across the second generation HRA methods, and these methods was based on the cognitive processes. So cognitive processes that has been used in the second generation HRA techniques for representing human error and field studies, that is the observational studies, case studies, and questionnaire study. So these methods are static assessment technique and used advanced assessment methodology. But slowly, the researchers observed that there is much inconsistency in the HRA results which has been obtained by different experts for the same problem. Although the researchers has tried sophisticated mathematical tools like fuzzy set theory, rough set theory, and other to reduce the inconsistency in the results as well as to improve the validity of the result. Now, after the second generation technique, we come across the third generation of HRA methods, which use cognitive architecture to simulate the human cognition process by cognitive modeling, which is basically a computer simulation. The evaluation process of an event and error, the dynamic nature of the PIFs, dependencies between the errors and interaction between PIFs are incorporated into the simulation for explicitly quantifying human performance probabilities. So here, researchers mainly depends on the Bayesian network techniques to tackle this intricate work at hand. These third generation HRA techniques are well constructed explicit method for assessing human reliability using dynamical modeling system based on the virtual task context and even with virtual operator. Now we come across certain issues in the quantifying the human error. So if we think about the human being as a machine, so we probably do a blunder, we can say, because machine, it most of the cases it repeats, it has repeatability, but human, it is case to case, it will vary. Today he is behaving in some way, another day with the same situation he is behaving in a different way, or in the same situation different person will behave differently. So we can say that it is difficult to assess person-based influencing factors like your bias, moral, motivation, and attitude. So these things are very difficult to model. Secondly, there is a probabilistic uncertainty due to analyst judgment. If we go by the judgment basis, so there is a probabilistic uncertainty on the input factors, and there is epistemic uncertainty due to limited experts' knowledge on relationship between the input factors. So it is subjected to both issues with the probabilistic uncertainty as well as the epistemic uncertainty. Third is, now during human error modeling, the analyst must consider dependencies between different types of human errors. There are several types of dependencies, including the likelihood that one human error contributes to or it may cause another human error. The likelihood that one person makes the same error repeatedly, that is, he reads all the displays incorrectly, or the likelihood that one person make an error that in turn increases the likelihood that a second person will make an error. So there is dependencies between different types of error, and dependencies are very difficult to model. And there are only a very few HRA methods that provides, or that you can say guide, to address these dependency issues. Fourth is, these third generation HRA methods are basically times and resource intensive. It analyzes human reliability without much emphasis on individual inferences or individual differences. The cognitive architecture used in the third generation HRA method is constructed based on the numerous facts which has been derived from psychological experiments, which have concerns about small sample size, individual differences, insufficient baseline practices, inconsistent methodologies, and the test sensitivity. So third generation techniques are subjected to all these issues. And another thing is that system safety that emphasizes analysis in addition to the past experience and codes of practices. So standards and codes of practice that incorporate experience and knowledge. The knowledge about how to reduce hazards. So these are usually gathered, these knowledge are usually accumulated over long period of time from previous mistakes, while the use of such standards and learning from experience is essential in all aspects of engineering, including safety. Now, today's the technology, the space it is changing, it does not fit to that. We cannot wait for such a long time to gather experience and to learn from the mistakes. So we are going to simulate the things so that you can say what is reliability, we call that accelerated testing. So here also we want to get as soon as possible the result from that one. We cannot wait for a long time to study and to gather knowledge by experience. So these are the issues in quantifying in human error. Now, challenges in the human error, that is hazards, these are not always caused by the component failure, and all failure that do not cause the hazards. And reliability engineering is considered mostly a design phase, and it concentrates on component failure as the cause of accidents. So human reliability assessment that required to be done throughout the life of an organization, and most working conditions have dynamic environment. Just a minute, please. Submission.
Participants, you can put your questions, queries in the chat box.
I'm sorry for the disturbance. So, challenges in incorporating techniques that are capable of real-time monitoring human capabilities into quantifying human error. So these are the different issues with the human error quantification. And what are the future directives? The prediction of human error before it occurs. This is one of the most challenging topic in human factors engineering research. So based on the quantitative analysis of multi-channel EEG recordings, it is possible to predict erroneous actions prior to error occurrence. So this transforms human error research work from traditional post-hoc analysis to real-time prediction of its occurrence with potential application of intelligent human error prevention systems. There is a need for portable and field deployable technologies for assessing mental workload in a precise, continuous, and reliable manner. Now, little is known about the varied effect of fatigue on human performance, and also there are scarce validated experimental model to identify the effects of fatigue on the human performance. So there is a scope to develop valid experimental models which measures fatigue that affect human performance. Now, I will give one such model for your human error quantification, which my group has developed. This model is based on the data collected from the field, that is mine accidents records. So from that one, so this is the flow chart of the model. So this is basically the estimation of human error through the retrospective analysis of accident reports. Now, to develop the methodology, here the human error, instead of human error probability, which is very, very difficult to calculate from the retrospective analysis of the accident reports, we have taken the human error rate as the calculation procedure. We have taken the human error rate per year. So this model is based on the assumptions that committing an human error. So error we have classified into the slips, lapses, knowledge-based error, rule-based error, as well as the violation. So assumption is that committing a human error leads to the mine accident. So either a error or a group of error has occurred, or they are the root cause of the accidents in the mine. So this is our assumption. On the basis of that assumption, we have developed the model. So the first thing, we select a sample of case study systems that representing the population of the mines. So naturally from the previous accident report, that is the past accident statistics, we selected some mines, like mines which are reporting the high accident rate or very low accident rate, as well as the average accident rate. So all types of mines we take in our sample, and that sample represents the population of the mine. Now we collect the accident records from these mines. Then these accident records, these are classified based on the unit operation in the mines, like your drilling and blasting, your loading operation, transportation, maintenance, like that. Now, each and every activity, we classify this accident record activity wise, as well as the your error type wise. Error type wise means we classify them into the 5 types of error which we discussed already. Now, from the literature, we developed a set of cues for each and every types of error. Now, from an accident report, when we are going through the accident report, we want to tally that which cues of which type of error is present during the accident, which from the accident report we are getting these things. So naturally, we'll get that maybe say a slip type of error, there are 10 cues which we have get from the literature. Now from the accident reports, we observed in a particular accident, there are only 1 or 2 accidents is present. Cues are present in that during that accident. So we can say that These accidents occur due to the slip type of error with a membership value of 2 by 10. So actually we have expressed all accidents as a fuzzy number. As a fuzzy number. So like that way, all the accident reports we express into a fuzzy number. Then we ultimately get a fuzzy sets of error rate, and from that we calculate the average error rate with average error type, that is for each type of mining activity, and for each type of human error we get a rate for that one. Now this is the estimation part of the human error. Now for prediction of the human error, we use a model which is based or which use the error rate which we calculated in the error quantification model. So here the assumption of this model is that human error rate, this is governed by the context of an activity. Now, how to define the context? Now, context that can be defined or described by a set of context describing factor. So in total, we enlist 11 such context describing factor, that is the context in which the mining works is done in the underground mines. Now we form a set of expert team A who will actually, now what is the effect of the context on the human error rate, that is not available. So we use the expert's opinion, that is, if the context is this, whether that will increase the human error rate or decrease the human error rate, or it don't have any effect on the human error rate. So like that way, we use the expert's opinion to study the effect of the context on the human error rate. Now, using the fuzzy mapping, we map the context on the human error rate. Now, this context, if there are say 11 context describing factors, and each context describing factors has different linguistic levels. Say I am telling one such context describing factor is working condition. So working conditions, we can classify it on the basis of the linguistic level, that is working condition is incompatible or it is compatible. So like that way, we get in total, there are out of 11 context describing factor, So 6 context describing factor was classified into 2 linguistic level, and 5 context describing factor was classified into 3 linguistic level. Now we can get or we can describe a context by combination of these different linguistic levels. So in total, we get such fuzzy rules of 15,552 for our total mining concept. That means we can get 15,552 such contexts in the mines. Now already we have calculated the influence value of a context on the human error rate. So for each and every context, we can get an influence value, and which is the best context and which is the worst context, depending on that one, which is the highest human error rate and which is the lowest human error rate, we are mapping that one. So we are getting a fuzzy causal relationship map diagram for each and every type of error and for each and every type of activity. Now, this context mapping diagram we use for the prediction of human error rate in a particular context. Say, we want to use that one for the prediction of human error rate in some XYZ some miles. So a group of experts will assess the values of the context in that mine, and depending on that one, depending on their responses of the experts, we will get the different context influencing values. Whatever values they have given to the context, depending on that one, what is its influence on the human error rate. So naturally, we'll get a influence value of the context, and that then we use the rough number, fuzzy rough number concept to get an average value, to get an average value of the context for the human error rate. So like that way, we calculate the human error rate in that particular organization. So these are the technique which we use into it. Okay, so thank you. That's all from my side.
Thank you so much, sir, for the nice presentation. So now I would like to hand over the session to Mr. Shobhik Das and Mr. Ashish Gar to complete the question answer session. Over to you both.
Thank you, Sinjana. Thank you, sir. The session was very informative and very interesting. We have learned a lot of things about human error and how you have used the fuzzy techniques. So, sir, we have got so many questions in the chat box. So, I am asking some of them. The first question is, sir, which cognitive approaches are used in calculating generalized human error classification? Yes, sir.
The generalized human error classification technique, this is the which I use, that is the technique given by the reason. So what reason use that one? So we classify that one on the basis of that is the 5 types of error. on the basis of the cognitive sciences.
Yes, sir. Yes, sir. Thank you, sir. Now the next question is, sir, how can you justify that the human error is the only key performance indicator in root cause analysis of any industrial accident?
We can say that the previous studies, it agrees that almost, I mentioned that 60 to 90% your system accidents or failure is occurring, the responsible for the human behavior. And whenever a system, this is my personal feeling, is that when a system is made by the people, so when it is failing, it is merely the failure of the human. This is human error, nothing else. Why so? Because you have designed the system. So either you did some mistake in the design stage, that your design was wrong. You may have choose a different, you have choose a not suitable material, or maybe there is a lack of knowledge. It is not from the point of view of the person that who is designing the system, he has lack of knowledge. Maybe that knowledge is not in the humankind. So we need more research in that area to improve our knowledge. So like that way, if we think that all aspects of the system life cycle, somewhere people are doing error because the system is made by the man. If we uh, ignore some incidents which we can term is by the act of the God, otherwise all are due to this is the system is made by you, so you are responsible for that one.
Yes, sir. Yes, sir. Thank you, sir. Now the last question, sir, I am asking, that is that what are the key methods for quantification and prediction of driver error in driving?
You see, most of the techniques, it is nowadays we are using the eye movement, eyeball movement, like that. That is the continuously. Basically, these are capturing the attention visual. So we want to use accept these things. Now one of my students is working on that one. That is, we want to capture the EEG signal on that one, and we want to capture the eye movement as well as the to measure the fatigue of that drivers, and to get a, you can say, composite measure from that one to check the person's suitability at that point of time, or in the real time monitoring what is his suitability for the driving. So by that way we can use that one.
Yes, sir. Yes, sir. Thank you, sir, for your explanation. Now I would like to invite Professor Krishna to formally provide vote of thanks to our expert speaker. Over to you, sir.
Thank you, Sinjana. Thank you, Savik. Professor Suprakash, a good lecture. Very, very interesting to practitioners, subject matter experts like me. You see, I remember 2004 when Tata Steel was having, in their own standards, many accidents in underground mines also, compared to, they have become almost accident free now. Literally accident free. Underground mines in Tata Steel are very, very little. So there is very different understandings about these human errors, unsafe acts, behaviors. DuPont has come up with with 200 years old their experience came with the behavioral based safety model, a 22 element behavioral safety model. They are the people who said behaviors could be measured. Behaviors could be measured and addressed by addressing the 22 elements, where most of the things which you said, all those things will cover. Very interesting. The subject is very interesting. Is a lot of things could be done. Thank you for bringing a lot of things. You started with system engineering and behavioral science. Very important for human. I fully agree with you. System engineering and behavioral science, but behavioral science itself is a big issue itself. But nowadays, many things. You see, I see in industries with huge number of accidents have come almost negligible now by putting very engineering interventions wherever human can make an error. Wherever human is the scope of making error, which has got big consequence, industries have come with the engineering interventions. And very successful. Very successfully it is done. So very interesting. All these things you must be working with the industries, all your models, and industries are looking for a positive approach. By doing this, the incidents will come down. That is the thing. That's what I keep telling Professor Maiti. So we all can work together in CoE-SEA. Your expertise, Professor Maiti's expertise, Professor Bhattacharya's expertise should help the humanity industries. Thank you very much. Thank you, audience, for putting very good responses, questions to the speaker. So we'll keep in the next 1 or 2 months. We'll get many behavioral-based safety speakers. They will bring different concepts of behavioral-based safety and how it is addressed. Industry speakers we are going to get who will tell the success stories of behavioral-based safety. And Sanjana, good. You did a good job. And finally, IIT giving this platform and helping all the people, academicians and industry across the globe. I feel really happy when I get so many requests from the industry specialists that we want to contribute in your CoE. That shows that these weekend talks are doing good, and many organizations are using these talks as competency building to their officers, and very good. Professor Suprakash will be in touch with you. We require your association with us. All of us together, we can do a wonder. Thank you very much.
Sir, I am always ready to help or to serve my alma mater. In any position.
Yeah, that's great.
Thank you. Thank you so much.
Happy to see Professor Ashish Bhattacharya and his two able disciples here. You three are doing great job in safety. Thank you very much. Professor Maiti, you want to say anything?
Thank you, Professor Gupta. Thank you for giving the wonderful lecture as well as accepting our request to help us in future. We'll look forward. We'll be in touch.
Thank you.
Thank you.
Thank you.
Thank you. Good night to all of you. Enjoy.
Good night to all of you.
We'll meet again next week, Friday, same time, with different speaker. Next time we'll have industry speaker, a beautiful speaker. Alternatively, we are arranging one academic speaker, one industry speaker. Next week, we'll have industry speaker. So till that, good night to all of you.
Thank you. Thank you, Professor Krishna. Good night.
Good night.